Hello Math Tours, welcome to the latest exciting Math 2 video. This one is on Incenter and Circumcenter, and that's section 4.3 in your textbook. Please have notes, some paper handy so you can take notes, and let's get started. First, we're going to start with a couple definitions. The first one is something called concurrent lines. Concurrent lines are three or more lines that intersect in a single place. So here's a picture, and the point where they come together is sometimes called the point of concurrency. Point of concurrency. And those three lines are concurrent lines. The perpendicular bisectors of a triangle. So if we have a triangle, we can draw lines that are both perpendicular to a side and bisect the side. So line M here, this line M, intersects this side at its midpoint, as denoted by those little markings there, and we know that that's a right angle, so it's perpendicular to side BC. So line M is the perpendicular bisector, or is a perpendicular bisector of our triangle there, ABC. The perpendicular bisectors of a triangle are concurrent. So we have three of these guys, and they all intersect in one point, and that point of concurrency is called the circumcenter. So this is the first of what we will learn of four centers of triangles, the circumcenter, point F. And one interesting note about the circumcenter is that it is actually the center of the circle that is circumscribed about the triangle. So there's a circle that goes around the triangle and intersects the vertices, each of the vertices. And the center of that circle is that point of concurrency, point F, the circumcenter. So that makes that point equidistant from the vertices of the triangle. Since F is the center of the red circle here, that means if I were to draw a radius to each of the vertices of my triangle, they would all be the same, of course, because no matter where you draw a radius in a circle, it's the same length. So we would say the circumcenter is equidistant from the vertices of a triangle. So let's look at an example. If we have the coordinates of a triangle, we would like to know where the circumcenter is located. So I have point A, B, and C, and if I draw them on a graph and connect them, creating triangle ABC, we could find the location of the circumcenter. It's particularly useful, easy, if one of our sides is horizontal and another side is vertical, because line or segment AB or side AB of our triangle being horizontal, I can draw a perpendicular line to it by drawing this blue vertical line. And since the distance from A to B is 1, 2, 3, 4, 5, 6, 7, 8 long, I can go over 4, and that's the midpoint of the side, and then drawing a vertical line here creates a perpendicular bisector. And then by the same token, if side BC is vertical to begin with, then drawing a horizontal line is perpendicular to it, and the length from B to C is 4, so I can bisect it by going down 2. And there's actually a third perpendicular bisector on the hypotenuse side here, AC, but we don't need that because we know that the circumcenter is the point of concurrency of all three lines. So if I were to draw that, it would be something like that. But it's not necessary for us to find the location. We just need the two that come from our horizontal and our vertical lines. So the location of this point right here is the answer to our question. The location of the circumcenter is at 6, 5. Here's another for you to look at. Same idea. If we have 3 points of our triangle, P, O, and S, located at these places, what is the circumcenter, or where is the circumcenter located? If you'd like to pause the video and give it a shot, go ahead. So I'm going to go ahead and solve this. I have OP is vertical. It's 6 long, so I go up 3 and draw a horizontal line. And then OS being horizontal, it's a length of 4. I can draw a vertical line at 2. So those are both the perpendicular bisectors. And this location right here is my circumcenter. And that is at 1, 2 in the x direction, 3 in the y direction. It's the location of my circumcenter. We have a town planner who wants to locate a new fire station that is equidistant from an elementary, middle, and high school, and we're interested in where that should be located. We know now that the circumcenter is equidistant from the vertices of a triangle, so if we were to draw a triangle from the location of creating a triangle by the locations of the 3 schools, we could then draw perpendicular bisectors of each of those sides, and the point of concurrency of those perpendicular bisectors would be the center of the circle, this circle. It is equidistant then to each of the schools. So we need to identify where the circumcenter is located. So let's change colors here. If I draw a perpendicular bisector of side HM, and then I do it again from side HE, roughly. Missed a little bit, but you get the idea. And then again, from E to M, get off of there. That point right there, that point of concurrency, is the location of the circumcenter, and so it is the same distance from the elementary school and the high school and the middle school. So that would be where we would want to locate the fire station. Our next definition is another center of triangles, another point of concurrency, and it's called the incenter. And the incenter is located at the point of concurrency of the angle bisectors. Angle bisectors. So my angles of my triangle here are bisected. So that means angle BAC is cut in half, angle ABC is cut in half, and angle ACB is cut in half. So point D then is called the incenter of that triangle. An interesting thing about the incenter is that the incenter is the center of the circle that is inscribed in the triangle. The inscribed circle is inside the triangle. Circumscribed is outside, inscribed is inside, which means then that the incenter is equidistant from the sides of a triangle, because each of these radii are, of course, the same length. And the shortest distance between the point and each side is the radius drawn to it perpendicular to the side. Okay, so the incenter is equidistant from the sides. Looking at an incenter example, so we have triangle ABC here, and we have the incenter drawn. I know that it's the incenter because all the angles are bisected here. These little arcs are showing me that the angles are cut in half, which makes G the incenter. So that means that the length from G to each of the sides is the same because it's the center of that circle. So GE is 2x minus 7. That length there is 2x minus 7. And GF, the same distance, is x plus 4. So if I solve this equation, I can substitute for x and find the lengths of those little segments. We're going to subtract x from both sides, add 7 to both sides, and x is 11. I can plug 11 in either place. I should get the same answer. So let's put it in where it's simplest. 11 plus 4 is 15. So each of these lengths are 15. Then GD is 15. Another similar example for you to try. I want you to pause the video and give that a shot. Okay, so I have QN is 5x plus 36, and QM is 2x plus 51. Let's solve by subtracting 2x from both sides. Let's subtract 36 from both sides. And then we'll divide by 3. So my x is 5. I'm interested in QO. QO is going to be the same as QN or QM, so I can substitute 5 in anywhere. Let's put it in where it's simplest here. 2 times 5 plus 51, 10 plus 51. Each of those are 61 long. Thanks for listening. Ask your teacher lots of questions.